Start recording, darn it. On the Algebra 2 page, if you go down to the SBAC review, I added at the top, this is a link to the exact Desmos calculator that's used on the test. I'm going to go ahead and just make this the one we use in Algebra 2. There's a couple things different about this. The same one we were using yesterday, but it doesn't give you all the options that regular graphing Desmos gives you. You can only do those two things. And one thing you can't do on this is, let's see, there we go. Yeah. One thing you can't do is you can't solve an equation. Like if we want to do something like this middle one. If I set up if I just set up 3x equals 4 plus 5x, it used to give me a vertical line at the solution, right, on regular Desmos, but notice on this one it says plotting single variable implicit equations is disabled. It won't let you do that on the SBAC test because it's just too easy. But it really isn't that much tougher to just do this the other way. If we're trying to find the solution to an equation graphically, what was our strategy? Like if we're trying to solve 3x equals 4 plus 5x, how did we always do that? We did a lot of problems in class like that. So yeah, we graph the left side, right? So we're just going to say y equals 3x. Okay, there's the left side. Now what? Now what? Graph the right side. So y equals 4 plus 5x. And what do I look for? Yeah, the intersection, right? So the answer is at -2, -6, right? So we're looking for an x value. So what's the solution? -2, right? Thank you. Let's see, who's that for? Kyra. There you go, Kyra Ford. You can come up and get it later if you want. What's up? So without even graphing that though, think about the orange line. What's the slope? 3. What's the slope of the purple line? 5. So if the two slopes are different, what does that tell you about the lines? If they have different slopes, are they going to intersect? How many times? Oh, for sure, right? They're just going to intersect once. Okay, so what about this last one then down here? Let's do this in Desmos first, and then I want to show you a way to do this not in Desmos. This is kind of the next topic. This is a little bit new. So if I graph y equals 2x, or the square root of 2x plus 3, and then outside of the radical plus 6, I get, where is that thing? Right there. So there's the graph, right? If I graph y equals 0, because that's the right side of the equation, do those ever cross? So what's the answer? No. Which one of those would I check? No real solutions. Yeah. Okay, how come? Well, the graphs didn't cross. What if we don't use the graphs? So we already know that this is the answer. How come? What do we do with this? Well, if we start with the equation, okay, well, let's just go down here. Okay, if we're starting with that equation, we're going to solve this thing. Okay, this is what we call a radical equation. Here, I'll rewrite it. Square root of 2x plus 3 plus 6 equals 0. Okay, if we're solving an equation involving a square root, think what we got to do. We're going to try to get that x by itself. Think about the steps we'd have to go through to get the x by itself. What would we do first? we'd subtract 6. And really all we're doing here is we're just going to reverse order of operations, right? So outside of any parentheses, we're going to subtract first. We get rid of the 6, push that to the other side. Now what? Yeah, now we've got this square root to deal with. Well, remember yesterday we talked about how a square root really is just an exponent. It can be written something, a square root of something is the same as that to what power? 1/2. Okay, so this really is just like an exponent, right? So as we work our way up order of operations, the next thing we hit is a square root, which is an exponent. So we got to undo the exponent. Well, how would we undo a square root? We'd square it. Yeah, we'd square it, and that's going to undo the square root, right? So we can come up with a really simple strategy then for solving equations like this. The first thing we're going to do is we're going to isolate the radical. Here we did that by subtracting 6 from both sides. We got to get the radical by itself on one side. So for us, that means just subtracting 6 from both sides, and that's going to give us the square root of 2x plus 3 equals -6. Once we get the radical by itself, we decided because that's an exponent, we got to undo the exponent. That just means squaring both sides. So step 2. Square both sides. What if it was a cube root? What would I do to both sides then? Cube both sides, right? But we're going to be working with square roots. So if I square both sides, that's going to give me, what does that give me on the left if I square a square root? Just cancels the square root, right? So I'm going to get 2x plus 3 equals, what's -6 squared? 36. Okay, that gives me a simple equation to solve, right? So what's probably the last step then? Isolate x, yeah. So the last step is going to be solve for x, but there's one important thing we have to include that you wouldn't normally anticipate. So solve for x and check solutions. Okay, why do you have to check the solutions? It's not just because you want to see if your answer is right. It's different. It's because when you square both sides, right here, I'm going to put a little asterisk there. When you square both sides, you can introduce what we call in math extraneous solutions. Extraneous is just another word for false, right? So you could introduce these false solutions. So you got to check to see if they work in the original problem, because a lot of times they won't, right? It'll give you these, you think you got it right, but you didn't. So this is pretty easy to solve. What are the 2 steps to get the x by itself? Subtract 3, it's going to give me 33, and then I divide by 2 and I get 33 over 2, right? So we get x equals 33 over 2, that's bad too, but we got to check that, because it may or may not work. So we're going to go ahead and plug it back into our original equation. So if we check it in our original equation, right here, if I plug in 33 over 2, I'm going to get the square root of 2 times 33 over 2. Well, the 2's cancel, right? Plus 3 plus 6 equals 0. So 33 plus 3 is 36, so I get square root of 36 plus 6 equals 0. Well, that's 6 plus 6. Does that equal 0? No. So what's that tell us? Yeah, it didn't work, right? It didn't work. This one solution we got was extraneous, so it doesn't count. And so sure enough, we end up getting what we now know that we were supposed to get, which is no real solutions, right? So you got to check. Let's practice that a couple times. Like, what about this one? So let's follow those steps here. What's the first thing I'm going to do to this one? Isolate the radical. Okay, so step 1, iso radical. What's that look like? Subtract 5, so I get the square root of 3x plus 9 equals negative 4. Okay, right away, just tell me, let's make a guess here. Chris, you're not getting a lot right there, I don't think, in that position. That's a little better. I like that. So what do you think? Am I going to be able to find real solutions that make that happen? You may not see this, but I mean, there's something weird about that. Something there that just isn't possible. What is it? Say it again.
They're not all like multiple the same. Not greatest common factor.
Okay, no greatest common. Okay, that's true. But just think about, without even looking too specifically, if I take the square root of something, if I plug a value of x into that, I'm just going to get a number under the radical, right? It's got to be it can't be negative, correct? Because we know it can't because we can't feed a radical negative numbers. We're going to get real answers, right? So I'm just going to put some number in there. If I take the square root of a number, what are the possible outputs of a square root function? Square root of 0 is 0. So I could get 0, but if I pick any other number, what can you tell me about the output? Square root of 16 is positive 4, right? No, just 4, right? The square root of 16 is just 4. If I'm solving an equation by square rooting both sides, I might have to take plus or minus the square root of 16. But the square root of 16 is just plain old 4. Okay? Square root of 25. 5, right? Square root of 10. Some decimal, but it's positive. Am I ever going to get a negative output? No, I'm never going to get a negative output, am I? Right? So you can see right away, you might see this, because I've got a negative number there that a square root is equal to, what's the answer have to be? Are there any values of x that could make that happen? No. So you can already tell, maybe you see this, that you're going to get no real solutions, right? You can already tell. But let's go ahead and just do the math to prove that. So we isolated the radical. What's step 2? Square it. So if I square both sides, that's going to undo the square root, so I'm going to get 3x plus 9 equals, what's negative 4 squared? 16. So now I solve for x, right? Solve and check. So what are the 2 steps in order? Subtract 9. What's that going to give me? 7 divided by 3. So 7/3. Let's check it and see. If I plug that back into my original equation, I'm going to get the square root of 3 times 7/3 plus 9 plus 5 equals 1. Let's see if that works. Well, 3 times 7/3 is just 7, right? So I get square root of 7 plus 9 is square root of 16. Well, is that going to work? No. Square root of 16 plus 5 is not equal to 1 because the square root of 16 is 4. So it didn't work. So the one solution we got to cross out. It's extraneous. So we get none. Okay? What about something like that? What would I we don't have to do the whole thing, but what would I have to do to solve this one? Dustin, why don't you close that up? This is more important. What am I going to have to do what's the first step going to involve? Okay, I got to get the radical, right? Isolate the radical. So I heard somebody say multiply by 3. Right, so that's good. I could multiply both sides by 3 to get rid of that. Then what? Divide by, no, negative 2. And that's going to get the radical by itself. And then I'm going to get some number on the other side. Then I'll square both sides, solve for x, and plug it back in, right? Okay, no biggie. Let's do one like this. This is a little different because now we have an x on the other side. Okay, so step 1, isolate the radical. Done, right? It's already isolated. Agreed? Okay, so step 1, I've already got that. Square root of negative 2x squared plus 48 equals x. All right? Step 2. square both sides. Okay? Cancels the radical, right? So I get negative 2x squared plus 48 equals x squared. Now I got to solve that. Well, that's this quadratic equation. What am I going to do in this case?
Move your 2x squared.
Okay, good. Move the 2x squared to the right. We'll add up like terms. So if I add 2x squared to both sides, I get 48 equals how many x squareds? 3x squareds. Okay, now what? Divide by 3, so that's going to give me 16 equals x squared. So now what? Square root. So I'm going to get x equals, but I got to do plus or minus now this time because I'm solving, I'm taking the square root of both sides of an equation, right? So I got to put plus or minus the square root of 16, which is 4. Okay, so those are my two solutions. Let's check them. So first we'll check x equals 4. So if x equals 4, if I plug that back in, I'm going to get the square root of negative, what's 4 squared? Negative 2 times 16 plus 48 equals x, which is, in this case, 4. So that's going to give me the square root of negative 32 plus 48 is the square root of 16. Is that equal to 4?
Yeah.
It is. Check. So that one checks out. Okay, let's try the other one. What if I try x equals negative 4? Same kind of thing. Negative 2 times, what's negative 4 squared? Positive 16. Plus 48 equals negative 4. Well, that's same as before. That's going to give me the square root of negative 32 plus 48 is 16. Is that equal to negative 4? It is not. So this one, we got to cancel out. So we only get one solution at x equals 4, right? Okay, what's the only difference with this one? One more we'll look at here. Same kind of thing. The square root is already isolated, right? So we're going to square both sides, but the problem is, it's not really a problem. We just have to be careful. We're not just squaring x, we're squaring x plus 1 this time, right? So step 1 is already done. We've got the square root by itself. Now when we get to step 2, I got to square the whole x plus 1 quantity, right? So on the left side, that's easy. Negative x minus 15. Now, what's this going to be? What are the ways I could get x plus 1 squared? I mean, I could. If you don't remember the pattern, what do you do? X plus 1 times x plus 1. Distribute the x, distribute the 1, add like terms, right? Hopefully you remember the pattern. What is it? That's like saying a plus b squared. What's that pattern? A squared plus what? No? No, it's not. A squared plus b squared is not a squared plus b squared. You can't distribute when you're adding stuff, right? What was that pattern? Unit 6 stuff. Maybe you're not done with that yet, but what's... No. No, the pattern is a plus b squared is a squared plus 2ab plus b squared, right? So if we go back up here, then that's going to be a squared plus 2 times a times b. 2 times x times 1 is 2x plus b squared. 1 squared is 1, right? So that gives us a quadratic equation. Now all we have to do is just, we're going to push everything to the right side. So we set it equal to 0. So if I add 8x to both sides, and I add 15, I'm going to get plus 10x plus 16, and it's all equal to 0. Let's just move it to the right. We just got to solve that equation. So we could use the quadratic formula, right? Do we need to? Are there magic numbers? 8 and 2. Good. So we get x plus 8 times x plus 2 equals 0. So what are my two possibilities? X equals negative 8 or x equals negative 2. Okay, so then we got to plug those both in and see what happens. Let's try that again. So if we plug in x equals negative 8, what's that going to give us? Square root of negative 8 times negative 8 is 64 minus 15, that's going to be 49. Negative 8 plus 1 is that true? No, it is not. So negative 8 we got to cancel. What about the other one? What if we try x equals negative 2? If I plug that in, I'm going to get the square root. What's negative 8 times negative 2? 16 minus 15. So square root of 1, is that equal to negative 2 plus 1, which is negative 1? No, because the square root of 1 is 1, and that's not equal to negative 1. So we lose that one too. Are there any solutions? No. Nope. No solutions. Okay? All right, so we got it. There's just a brief, but that's all you need to know, right? If you just remember, isolate the radical, square both sides, check your solutions, you got it. Did we do this one? Yeah. We finished it? Okay. Okay, last one. All right, see you guys up there in a little bit. Okay, what about this now? A leaf falls 18 feet from a branch to the ground at a rate of 5 feet every 2 seconds. Okay, so on these, what you want to do with stuff like this, I think, is you want to try to, we want to read the question carefully, and whenever you can, you always want to think of this in terms of a graph. You don't necessarily even have to make the graph, but we want to think of it in terms of a graph. So when we read through this thing, see if we can identify some stuff. A leaf falls 18 feet from a branch to the ground at a rate of 5 feet every 2 seconds. Okay, what does rate mean to us when we're talking about a math equation? Slope. Rate always means slope, doesn't it? So we know there's going to be a slope involved. And if it's falling 5 feet every 2 seconds, and we're measuring height, think about what the graph would potentially look like. For now, just think about what you would label the axes. That's really important. That's super helpful. So if we draw the x and y axes, what's represented by the y-axis in this case? What are the quantities that we're comparing? So we're comparing, what would you say? So it tells us 18 feet is what? How do you describe that? Height, sure, it's just like the height above the ground of the leaf, right? And so that's one quantity, is maybe height, right? And it's falling to the ground at a rate of 5 feet every 2 seconds. So what's maybe the other quantity? Time. Okay. So which one's going to go on the y-axis? Height, because you know time always goes on the x-axis, doesn't it? If time is one of the quantities, it always goes on the x-axis. So x is going to be time in seconds, and y is going to be height in feet, right? Just knowing that is really helpful, right? So now that we know what that looks like, well, if this is time, this is going to be time 0, isn't it? And then time is going to move to the right. So at time 0, what is time 0? That's like the very beginning, right? What's the height? 18. So 18, we recognize 18 is the initial value, or the start value, right? Start value is right there. So B equals 18, right? Because B is always our start value if we're going to make a linear equation out of something, right? So we know we've got over here at 18, we've got a point. What's the graph going to do? It's just going to go down, isn't it? We don't know exactly what it looks like, but it's going to do something like that, isn't it? Right? Yeah. Can we come up with some other points on the graph? Think about this. So we want to come up with some ordered pairs. Here's one ordered pair that is at 0, 18. So when t is 0 seconds, height is 18 feet. Can you tell me another point on the graph based on the information we're given?
32.
Okay, I heard 13, right? Because it's going to drop by 5 feet after 2 seconds, right? So there ought to be another point over here somewhere, like right here, let's just say, it doesn't have to be exact, which is going to have a t value or an x value of 2 seconds and a y value of 18 minus 5, right? Yes, sir?
Yeah, go use the restroom.
You may. Okay? And we could keep going with that, couldn't we? What's another point? Okay, we could go over 2 more seconds. We're going to drop down by another 5, aren't we? Right? So we could go over and we're going to get something like 4 and then 8, right? And then we're going to get, what's the next one? 6 and 3, right? And then after that, it's going to hit the ground before we get to the next one, right? So that's pretty good. That gives us a lot of information. So let's see if we can, let's see how many of these we can answer. So the initial height, thank you. Is the initial height 18?
Yeah.
Yeah, it is, right? That's true. Does the leaf fall at a rate of 2/5 of a foot every 1 second? It doesn't, does it? Now think about this. If it's falling 5 feet in 2 seconds, right? That's our slope, isn't it? That's our rate, 5 feet in 2 seconds. Here's what I would have you always do. I would always look at the number part, separate that. So the number part, 5 over 2 is just 5/2. So is that 2.5? Now what's the variable part? If we look at the quantities, at the units, we just get feet per second. So the rate is 2.5 feet per second, not 0.4 feet per second, right? Okay, make sense? So that one is false, right?
True.
Is the leaf 3 feet above the ground after 6 seconds? Yeah, it is, right? That fits. Okay, now I'm going to show you something here that's really cool. You got to really pay attention to this. This is something on Desmos that you can do this makes a lot of these questions really simple, okay? It's a trick. So on Desmos, one of the things you can do is you can make a table, right? So we could say, let's see, how am I going to do this? So you go up here to this thing and you add a table, okay? It gives you one column named X1 and one column named Y1. When you have the sub 1 there, it just means we're going to pick individual values. Chris, please put that away. So what are some values that we know? Well, we know that when X is 0, we already figured this out. When X is 0, because X is time, the height is 18, right? You guys immediately told me that after 2 seconds, so when X, which is time, is 2, the height was going to be 18 minus 5, which is 13, okay? All right, so now I'm going to show you something you can do here that's really cool. If you go down to the next row, you can do what's called a regressional analysis. You don't even need to know that that's what it's called. That sounds really fancy and scary, but it's not a big deal. There are my 2 points, right? If I want to come up with the line that goes through those 2 points, all you've got to do is go y is, I think you do y1. Y1 is, you don't say equals, you use the little tilde, which is like shift, and then it's to the left of the 1. It's that little symbol. That's the symbol you have to use. So y1 is predicted by, is what that means. The best fit line, which is just mx1 plus b. That's all we did, right? So in this table, we're just saying y1 is predicted by mx1 plus b. Same every time. And look at all the stuff it gives you then. it tells you that the slope is negative 2.5. Yeah, that's right, Negative 5 over 2. It's going down 5 when it runs 2. Tells us that B is 18. Correct. Okay. If we want to, now that we know what M and B are, look what we could do. We could say, okay, well, let's make a function. F of x equals the slope, right? Mx plus B. And look what it does. It gives us that line, but now it's a function. So if I want to plug in any values I want to, I can say f of 1. And it tells me it's 15.5, right? See what I'm saying? I could pick f of 2, and it tells me it's 13, right? So I can plug in any values I want to on that thing. Does that make sense? Okay, so like in this question, what question were we answering? Well, for one thing, it wanted us to know what's the slope. The leaf falls at a rate of, that's our slope, 2/5 of a foot. Well, that's per second. That's wrong. The slope is negative 2.5, not 2/5, right? They want us to know, where is the leaf? Is it 3 feet above the ground after 6 seconds? Well, all I got to do is put in a 6 for my x, and I get back a y value of 3, so it's true, right? Isn't that cool? So you can come up with that best fit line that easily, just that one little trick. It gives you, all you need are 2 points, and from that 2 points, you can get the whole line, okay? I'll give you a chance. We'll practice that a little bit on Friday, okay? Uh-oh. Who's going to be gone Friday? A couple people? Okay. Go on Friday. Okay, well, I'll tell you what I'll do. I'll put a couple problems up that you can just do even like over the weekend, just to practice that. What's that? More of this. We're just reviewing for the rest of the week. Okay. Okay, that's after SBAC. Won't matter. All right, so moving on. Moving on. How much do we have? Oh, we can do one more. This is easy. Okay, last one. Last one. There we go. Quick, quick. Okay, so what about this? When they say something like this, enter an equation that can be used to find the speed, you don't have to do anything, hardly, right? All you got to do is just come up with the equation that we could use to solve for the speed x. So what are they telling us? A train travels 250 miles. What kind of quantity how would you describe that? A length or a distance, right? Okay, so we'd say, we'll call that d for distance, right? At a constant speed, x, well, speed, okay, we know it's speed, in miles, speed x in miles per hour. So we want an equation that can be used to find the speed of the train if the time to travel 250 miles is 5 hours. So 5 hours is t, 250 miles is d, and the speed is just the rate, isn't it, right? What's the equation that we always use to relate rate to distance and time? Do you remember that? There's a couple ways you can think about it. So speed, we'll call speed s. How do I find speed? Speed is distance divided by time, right? Think about how you measure speed in miles per hour, right? If you travel 50 miles in 2 hours, what's your speed? 25 miles per hour, right? You got that. So speed equals distance over time. So all we'd have to do if we want to enter an equation that can be used to find the speed, let's plug in those values, right? Okay.